And hello, welcome back to today's edition of Radiation Heat Transfer Learning Journal. And in the last video, we're talking about some heat transfer between black surfaces, and we know that this kind of heat transfer between black surfaces is kind of our baseline because it approximates what a real heat transfer situation would look like. All right. Now we want to add a little more realism to it. So instead of a black surface, all right, we want to consider heat transfer between two arbitrary gray surfaces. So gray surfaces are slightly more realistic than black surfaces. Okay, so now we want to derive expressions for heat transfer between gray surfaces. Okay, and these are diffuse gray surfaces. Okay, so directionality doesn't quite matter. Okay, so gray surfaces. Okay, gray surface. What is the difference between the gray and the black surface? Okay, so gray surface does not absorb every bit of radiation incipient on it. So you have some radiation, HR, the incipient one. Okay, so for a black surface, everything is absorbed. However, for a gray surface, some of it is reflected. And what is this row here? This row is the reflectivity. Okay, the reflectivity is the fraction of radiation that's being reflected off the surface, and the rest of it is of course absorbed. Okay, the absorptivity. So how much is absorbed into the system? Okay, we assume it's opaque, so there's no transmissivity. How much is absorbed is equals to alpha HR. For black surface, absorptivity is 1 and reflectivity is 0. Okay, so I'm gonna put this here. So this is recap on gray surface. Recap on gray surface. Okay, so recap on gray surface, this is what it does. There is reflectivity and absorptivity. So let's just do a typical energy balance again on one of these small little areas. Okay, the A1, and of course we have the A2 here. We shall use a different color, the A2. All right. Okay, so let's see. Yeah, let's see. So gray surface. Okay, so this is what a gray surface does. We want to do an energy balance across the A1. Okay, so energy balance, right? What is the net heat coming off the thing? Okay, so there is, according to this diagram, what's coming off this thing? This is will be the emissivity times EB. Okay, because there will be some heat that's being radiated off. EB. Okay, so let's go and put dA1 first just to make it clear. So this is the emissivity into EB T dA1. Alright, why is there this emissivity here? Emissivity is the ratio between the amount of heat that is being radiated by a black surface. Okay, so let's recap. Emissivity equals to heat emitted by surface versus the heat emitted by black surface. Okay, So the heat emitted by the black surface is this much, EBT times dA1. You multiply that by the emissivity, you get the heat emitted by whatever surface this is. So this is the radiation coming off this surface by emission plus reflectivity, the reflected part. And for a gray surface, the reflectivity, the reflected radiation is kind of scattered equally in all directions, just like the emissivity. That's why it's called diffuse. Okay, diffuse is a diffusely reflecting surface. So I'll just put rho into HR dA1. So HR is whatever incident radiation is coming in, and the portion that is reflected out is rho HR. Hopefully that is pretty simple and straightforward. So this is a diffuse surface. For diffuse surface, for diffuse gray surface, this is the characteristic formula. And what kind of surfaces are diffuse? What surfaces are diffuse? Well, you can imagine for a mirror, you can imagine the surface is very smooth. Okay. Let's get this here. Okay, let's see. Yep, okay. Let's say you have a surface, a perfectly smooth surface. If you have an incident beam of radiation here, you have to take the angle. This is optics here. There's a beam of radiation coming here, and it will go off at exactly the same angle. I'm not drawing according to scale here, but this is a flat surface, right? If the radiation is coming in like that, it will scatter off at the same angle. But how do you then get a diffuse surface? Well, if you have a very rough surface with lots of jagged edges and all, okay, so you have, let's say, this beam of radiation coming in, right? Then it would find this angle, it will bounce off at this angle, right? If you have another beam of radiation coming in here, it would find this angle normal to the surface and bounce off at this angle. Alright, so if you have a surface rough enough and the surface is very rough, it will emit diffusely. So rough surfaces emit diffusely. So this is a good approximation, this for a real rough surface. Okay, so anyway, back to this. This is the net radiation that's coming off due to the emission bit and the reflected bit. And what else? It still has to receive radiation, right? It has to receive radiation. So since it receives radiation, how much radiation? Anyway, sorry, was minorly wasn't distracted. Anyway, back to this. So we need to consider the radiation incoming. So what's the radiation incoming? That will be 1 minus the reflectivity into whatever is normally incoming for a black surface, right? So it will be this whole thing magic here. Okay. Or rather, let's just use the term HR. 1 minus rho into HR. So yep, we have to multiply that by the area dA1. And we know that I think we have to do a subtraction here, because that is the amount received, right? That's the amount received. So it's 1 minus the reflectivity, and that goes into HRDA1. Let's check whether anything is what our yeah, what this is. Okay, so we see Oh, oops, I think I made a mistake here. So anyway, let's revisit this again. The net radiation coming off the surface is equals to the the amount emitted, the amount reflected, and the amount received. What is the total amount received? This is the amount being absorbed, right? And I will also have to account for the fact that there is amount reflected. So we look at the energy balance across the surface again. So the gray surface will emit some amount, and there'll be some reflected amount. Okay. And the total amount of energy entering this control volume, this will be HR. So whether it's reflected or emitted doesn't really matter. The amount of energy being received is HR. So this is what's going in, this is what's going out. Don't worry about the reflections or any other kind of thing. So this has to just be as such. Okay. And okay, if we actually combine these two, this is just 1 minus 1 minus rho HR into dA1, and equals to, that will be minus alpha HR dA1. So what am I saying here? The amount the net amount being absorbed is equals to 1 minus reflectivity times the amount of incipient radiation. And if we were to take into account that radiation on this surface, the opaque surface, is either radiated or absorbed, we will note that alpha plus rho equals 1. So that's how we get this expression here. Okay, we kind of want to simplify our analysis because we don't want to keep into account what is radiated and what is reflected, if possible, what is emitted and what is reflected. We always want to simplify our analysis. And for gray surface, because the spectrum doesn't matter, okay, there's no black body spectrum that we need to take into account, what frequencies. And in fact, conveniently for gray diffuse surface, the reflected radiation will go diffusely everywhere, and the emitted radiation will also go diffusely everywhere. So it is convenient. We can't actually differentiate, for that matter, between emitted radiation and reflected radiation because it is diffuse and it is gray. So what's a convenient thing for us to do is basically to combine both of these terms here, the emission term and the reflected term, into this term called radiosity. Okay, and this is very important. Radiosity, JR. This okay, so I'll just write here, this is the combined emitted and reflected radiation coming off a surface. Now for a black surface, this is a special case. It's a special case of JR equals to EB. So the radiosity of a black surface is just the black body emission because it doesn't reflect anything, so the reflection term is 0. Okay, so that's the radiosity just happens to be the black body emission for a black surface. So if we move this thing down here, okay, we can replace this whole thing by JRDA1. Okay, so I'm just going to write that down. And we will have something that looks pretty much like our black body radiation equation. So QNet DA1 equals to JR minus HR. And we take a look at the black version, the black body version. Yep, and we find that QRDA1 equals to EBR, this is the radiosity equivalent, and minus HR. HR is all of this here, which is H0R, which is the external radiation, minus the contribution from the other surface, which is this term I'm highlighting here. So the question, of course, is what is HR for a gray surface? Next question is what is HR for gray surface? Okay, so I think that's going to be the discussion in our next video. I'm going to stop here, and I'll see you guys next time. Bye bye.